today's topic will be. So we continue these basic methods of linear algebra, which are focused. So in here, so it's real, no? So everything will be real. It also works for complex, but with little modifications. So let's just consider a real case. So that here Q is orthogonal matrix. It's an orthogonal. Is orthogonal. And remember, orthogonal means that inverse coincides with the transpose. And the geometric meaning of the orthogonal matrix is just rotation in m-dimensional space or reflection. And R is upper triangular, upper triangular. So remember upper triangular, but it's m by n. So if it's m equal n, so it's square matrix. So upper triangular means that the elements are on a diagonal or above. But now there are other two cases. So if m is bigger than n, so more rows, then upper triangular means everything is relative to diagonal, which starts from the left angle. So if m is smaller than n, then it will be like this. So this is what it means. And the idea, actually the change from LU to QR is that we use the use of orthogonal matrix. So remember that we already learned that condition number of orthogonal matrix, condition number with respect to the usual product, usual norm. So condition number of the orthogonal matrix is 1. So this is very good. This is very good situation because by every time by factorizing the matrix into two parts, you lose the precision, because you multiply something. And we know that the error is amplified by this condition number. So in this case, when Q is orthogonal, the condition number is 1. So we essentially almost do not lose anything. And this is because, so geometrically what happens is that A is a linear operator for linear map from Rm to Rn, and now Q is from Rm to Rm, which is just rotation. So we just change coordinate by rotation in the first space, and this gives us this decomposition, and the rest is upper triangular. So this is this helps for solving linear system. So in standard way. So let's take here m equal n, right? Same number of equations is unknown. So with solving, you just substitute that A is QR. And now if you multiply from the left by transpose, so you remove the first Q. And you get this equation by directly. So right hand side, you just rotate vector B. And here, this is the first part is upper triangle. So we know that this equation is solved explicitly by the method of back solving. So backward substitution. So you solve the first, and you solve the second, you solve the third, and so on. So this is how it's used. So whenever you succeed to make this decomposition, you easily find the solution. And you find it very well because so Q is orthogonal matrix, so you almost don't lose precision by this at least by the operation of this decomposition, by performing the decomposition. Okay. So there are several methods to find QR. So given matrix A, we need to find matrix Q and find matrix R. There are different methods. So I will just explain one method, which is not exactly what is usually implemented in programming, but at the same time, it's a method which is easier for the analysis. So we take one of the methods. So this will be Gram-Schmidt procedure. And we just consider M equal n, so it's n by n matrix, and which is non-singular. The matrix A is quadratic non-singular, so let's show how you make this, how you perform this decomposition in this case. So okay, so matrix is non-singular square, so it has exactly n columns. So let's just denote them by small a. So each a is a column. So it's columns. Okay, so what we do? So they are columns and they're linearly independent. Because we assume that matrix is non-singular. So in general, they can be linearly independent, but here it's linearly independent. So what we do, we take we compute a system, a set of orthogonal vectors, mutually orthogonal. So from a set of vectors which are arbitrary but linearly independent, we can compute a system of orthogonal vectors. In the following form. So the first vector, what we do is this Gram-Schmidt procedure is you take the first vector as it is, and then you modify the second so that it's orthogonal to the first, then you modify the next so it's orthogonal to the rest, and so on. So you just make it sequential. So the first vector we don't need to change. But from the second vector, we have to subtract the path which is tangent to A1. So it becomes orthogonal. So we subtract A1 by proper coefficient. So 2, 1, no, 1, no, 1, 2. With a proper coefficient, which is just projection of A1 to this direction. So alpha 1, 2 is a projection. So we have to project it A2 by project to Q1. Dividing by the norm. A little better, let's just write norm. So what you can see is that you can see that Q1 and Q2 are orthogonal now. So what we did is there was a vector A1, the vector A2. So what we did, we projected and removed this piece. So what will be left is Q2 is exactly the part of the A2, but in orthogonal direction to the previous one. So the next, and so on. So at every vector qk, so you take ak, and you subtract all the projections to previous directions. And then it will be orthogonal to all the rest. So it's minus sum over j from 1 to k minus 1. So the projection coefficient is jk, alpha jk, q, j. And the projection is just jk, should be a k, q, j, correct? Yes. Square. So here k is from 2 to n. So by construction, they are orthogonal. So qi, qj, the scalar product is 0 if they're different. But also, the norms of all of them are non-zero because original system was linearly independent. So original system is linearly independent, and by construction, you see that we always take the same vector here as the first term. So by construction, the new system is linearly independent, but since they're orthogonal, so neither, well, if you're linearly independent, it's automatically, so none of them is 0. Okay. So then what we do, we take this system and write it in a different form. So we take this system, which is, let's say, star. So star can be written in the form, so the left-hand side is, let's just take all of these columns and put them one after another. Q1, Q2, Qn. So these n columns. And this will be equal. And this part you can construct as a product of two matrices. So the first matrix will be columns of A. And the next matrix is exactly the coefficients. So the coefficients, see, so these are 1, 1, 1, 1. So we have 1 on the diagonal. And it will be minus alpha 1, 2, 1. No. So 1, minus 1, 2, correct. It's minus alpha 3, 3. Yeah. 1. And here everything is 0. So what you see is that we have this matrix A here. We have this matrix which we'll call Q with a tilde. And this is matrix which we call R with a tilde. So what you see that R is already upper triangular. And Q tilde is almost orthogonal, except that if you take Q transpose by Q, so what it is? It's a matrix of scalar products of Qi by Qj, right? And this is diagonal matrix. So this is diagonal matrix because they're orthogonal. So you only have it something Q1 here with a square Q2 square until Qn square. So it's a diagonal matrix. Okay. And this, so we can say that this is equal to D square, where D is diagonal of norms. Right, so D square gives you squares of norms. Okay, good. So in other words, so what we get is that Q transposed by Q is D squared. So what we can do is we can inverse this matrix D, because it's just 1 over each element, and multiply it by D minus 1 from both sides. Okay, and now let's let's write this part as transpose of this product, take into account D minus 1. So here you take into account that if you transpose D, it's the same D because diagonal. So it will be this D minus 1 Q D minus 1 equal identity, and now we call this Q. So we found some matrix which is orthogonal. Orthogonal. Okay, and now we will use it here. So now let's just write this matrix equality in a compact form. So it's Q tilde equal A R tilde. Also now remember that Q is, we have this relation that Q is Q tilde D minus 1, from which we can write that Q tilde, put D back here, so it will be QD. So we can write this relation. So let's start with A tilde equal QD. And now we can, we consider, remember what I wrote, that we consider non-singular matrix A, which means that R should be non-singular, so we can invert it as well. And this is QR. So where Q is already orthogonal by construction, and R is D R tilde minus 1. So this is diagonal. And R tilde was upper triangular. So whenever matrix is upper triangular, inverse is also upper triangular. And then multiplying it by a diagonal, it again keeps it upper triangular. So this is upper triangular. So we found a way. What we did, we first proved that this decomposition exists, right, for square non-singular matrices. And we also gave a constructive way how to compute the QR decomposition. Maybe not the best way from numerical point of view, but fully complete way how to do this. So as an exercise, rather simple exercise, you can think of how to extend the proof to the case of singular, of n by n singular matrix A. So what's missing for make it working for the singular matrix A? Just try to check. Okay, so now, so next step is I already showed how it is used, how QR can be used for solving equations, and the main advantage is this, so that the condition it's very well conditioned. So you're sure you keep your error small. And there is another application which is similar in spirit, but slightly, but not exactly the same, which is solving. So using QR decomposition for least square problems. Least square problems. So what is this least square problem? So I'll give you an example of how it may appear, though it may be in different ways. But essentially, the idea is when we solve the linear system for m by n matrix A, which is not quadratic, and m is bigger than n. So it's overdetermined problem. Overdetermined in the sense that m is a number of equations, n is a number of unknowns, so the number of equations is bigger than the number of unknowns, so it's in general no solution. In general, No solution. So why? So we don't have a solution. So why we still want to solve this to do something with this problem, even though it doesn't have a solution? So example is the following. For example, imagine that you have a function. Function f as function of time. You measure something in time. For example, meteorological station measures temperature at different moments. And you get your result at time t1, t2, t3, until tm. So you have m measurements, and at every time you got value y1, y2, y3, till ym. So what you have is that your function at time ti equal yi for I from 1 to n. Okay, so we want now to compute values at different points. So how you do it, you make approximation, and one of the ways to approximate is to use some basis in the functional space. So if you have a full system of functions, you can expand any function in this basis, but usually in functional space, the basis is infinite. So what you do, you cut it. So you take just finite number of basis functions and try to approximate this function with this basis function. So let's consider basis functions. Phi1 of t, Phi2 of t. And then there is some number of these functions which is different from n, right? Usually it's like m functions. For example, if you remember Fourier analysis, this could be sines and cosines until certain mode. And we want to fit the data for the approximation of the function as linear combination of these basis functions. We say that we want these functions is what we want to work with, and we get some data for some functions, and we say that we will now take a linear combination of these functions in order to approximate f. So we need just to have these coefficients, x1 to xn, and having this coefficient, we can compute what is f at any other point automatically. Good. So what we do, what means we want to fit the data? It means that we want that this equation will be satisfied at the points which we measured. So the data implies that f of ti equal yi, and now, for f, we substitute this sum. So the first equation will be phi1. So let's take first, right? Okay, I from 1 to m. So the first will be phi1, and we take f in this form. So the first will be x1 by phi1 t1 plus x2 by phi2 x2 t1, so on. This one multiplied by the vector x1, xn. It will be given so the second row is the same, but at time t2. Like this. And this is M. So this is matrix A, right? This is vector X, and this is vector B. So we have A, X equal B. So we reduce the problem of expanding our function into the certain system of basis functions from the data. So from the data. So we want to solve it. Again, so it's overdetermined. So if M is bigger than N, then in general there is no solution. But there is no solution. It's natural why there is no solution, because if we have a lot of data points, we cannot approximate a lot of data points with smaller number of functions. So here we should have M smaller than N, right? Is it correct? There's something. Yeah. It's all the way around. So this is 1 to M. N. So if M is bigger than N, yes. This is N. This is M, this is N. It's all the way around. So we have M here and N here. Yeah, and then this is up to N. Yeah, that's correct. So, so you see, we need to have more data, M. So the M is the number of data points, and N is the number of functions. So if data points are bigger than N, so no general no solution. This is because we don't have enough functions to fit it exactly. But often it's not good to fit it exactly, because points may have errors. So it's sometimes good to have, often it's good to have less functions. So we look for X star, which is not exactly the solution, but it's a vector of X, which give the vector such that this equation is solved in the best possible way, in some sense. So we find X star minimizing So minimizing what? You can put B on the left-hand side, then it should be something equals 0. So this is something we just minimize. So we minimize the norm of X minus B. So we minimize the norm of the difference. Okay. So why QR should be used in this part? First, let us solve this question directly, this problem directly. So we want to minimize we minimize the function phi of x, which is this norm, but instead of minimizing norm, it's better to minimize square norm. And just we took it 1/2 for the convenience. And now remember this will be 1/2 of the scalar product. And scalar product can be written as transposed times the matrix. Times the vector. So this is the scalar product. And now we just take a product. So the first term will be 1/2 x transpose A transpose AX minus 1/2 x transpose A transpose from here B minus 1/2 transpose AX plus BB. So normal. Now look, these both are numbers. These both are numbers, so you can, for example, take this as equal to its own transpose, because transpose of a number is the same. And now applying transpose to each of the terms, you see that this is exactly equal to the previous one, so we can put them together. And this is quadratic. This is quadratic function, quadratic form in X. So we know if we so it's smooth function. We know if we minimize then the gradient. So if the minimum, if we take minimum of the function, then at the minimum the gradient should be 0. So all derivatives should be 0. And gradient can be computed. So just take a while to understand how we compute. So when you compute gradient of this quantity, you just get this vector. And when you take gradient of this quadratic form, so you differentiate it twice with respect to the first and the last. And it gives the same, actually the same result. So essentially the check that what you get is ATA X minus ATB equals 0. So you find X star. Well, you don't need to inverse. So solving this system, already this system, you see, this system is already not overdetermined, because this is this matrix. Remember, this was n by n matrix, so is this n by n? This is n by n. So in principle, you can use methods and solve you obtain X star. So analytically, you just multiply by the inverse and you get a star. Let's write it explicitly. TA. Okay, so what we showed is that there is a solution, and it's actually even unique. So the problem is that this solution is ill-posed. Is often, let's say not always, ill-conditioned. So what does it mean? That the condition number of this matrix ATA can be very large. So condition number can be very large. So this method gives you a solution, but it's not a good numerical way to find the solution because it's ill-conditioned. So the good way actually to solve the problem is through the application of the QR decomposition. So let's take a small break. Let's take a small break and then we'll continue. Okay, so what we do for using QR decomposition is essentially the same thing, but with one extra step, which is Q. So using QR, what you do with the norm so we put QR in the place of A. Now remember that that Q is orthogonal matrix, so it's exactly the matrix from linear algebra. We know that it's metric of rotation or reflection. It is isometry. It doesn't change norm. So it means that we can multiply everything by Q. O is transposed, doesn't matter. So norm will not change. So because this is isometry. So the norm will be the same as the norm after multiplication by Qt. But QTQ is identity because this is orthogonal matrix. This will be R minus QTB. And this should be minimized. We forgot X, right? And we know that, so okay. But now R is upper triangular. Upper triangular, and remember, so we had M bigger than N. So what we had for R is that it's of this form. So it's M bigger than N. So this is M rows and N columns. So R is actually can be written as we split into two parts, which is upper part we called R tilde, and the rest is 0. Right, so this R tilde is n by n. So n by n matrix. And in similar way, we split vector B. Actually, we say that B with a tilde, which is QTB. And we are split in just the same way. So it will be tilde 1, B tilde 2. So the first n component and the rest. And then this norm. And the same for x, right? Do we need for x? No, x we don't need. So what we get from this norm, so the first part will be, so it will be two vectors. So it will be norm of the vector where the first part will be, it will be R tilde x0. And this will be minus B1 tilde B2 tilde. And you see that in the second part, it's just B2. In the first part, so just Pythagoras theorem. So it's some. So now let's consider square. Okay. So it's sum of the squares. So this is equal to the square of the first part plus square of the second part. And this is what we have to minimize, because this minimizes the first norm. So this should be minimized. But we don't care about this term because it's constant. So we only need to minimize the rest. And the good part is that it is already n by n. So there is no m. So if R tilde, which is n by n, is non-singular, then the minimizer of this is the solution is the solution star of this problem, yeah? Because if this problem has a solution, that is just 0, and it cannot be smaller than 0, so this is minimizer. And this problem we can solve by back solving. So this is upper triangular matrix, so we just square upper triangle, so we just by back solving find the solution. So this is a method of how you using QR. So essentially what you do, you use the fact that you can rotate the system to the upper triangular form, and then reduce it to the problem which is back solvable because it has upper triangular form. So at the moment, as soon as you get QR decomposition, the solving the least square problem become straightforward, and it's a good numerically from numerical point of view, because all pieces in this process are well conditioned. Okay. So this is it. So I'm giving selected topics from the book, not all the topics. So I think that maybe some topics you get on a numerical or on exercises. So my idea is that we will have intensive theoretical part until the beginning of June, so for two months, and then in June you will try to focus on some practical things, trying to create to solve something numerically, just to apply to see how it works. And this is where we will have splitting if somebody wants to have, because this course is supposed to be also doctorate course for those who want. So for those who want to have it as a doctorate course will have harder problems than those who want it as a master course. Okay, so I finished with QR decomposition. So the next topic is iterative methods. We have quite a big part of the book devoted to these methods. I will just give you an idea And probably next time we consider something more specific. I'm not sure. So essentially, iterative methods, they're usually convenient for very large systems. So it's often then there's actually a huge amount of application, especially engineering computations of engineering structures, of dynamics of continuum, and so there's a huge amount of problems when the problem of solving this this equation is hard not only to make computation, but even to store it. So sometimes you have, for example, the vector x, which is already 1 terabyte of memory. And then certainly you cannot store everything easily. So for example, you have 1 billion of equations to solve. So whenever you have to solve 1 billion or even more equations, all the methods like Gauss elimination and so on, they are hard to implement because there's a huge amount of operations that you just cannot do. So that means that just by computing limitation, you cannot solve this. You don't hope to solve it exactly, but you want the solution. When the solution with certain accuracy. So for this, even if we use Gaussian elimination, it's not exact solution, right? Because it's numerics. So we want to find a solution. So we can have iterative methods which do the job with less. Maybe it's not so precise, but with less resources, and more resources you get, more iterations you do, so better solution you get. So essentially, the idea is simple. So idea is that you take A and split it into two parts, m plus n, where m is special. So usually in the case, it's simpler. So simpler to solve the system mx equal b. So you split in A into two parts, where first part is something very simple, like, for example, upper triangle. So if m is upper triangular, then you solve any equation with m just by back solving. So it's just a clear procedure. So it's much less operations than solving with A, which is general. And so now we just need to treat this addition n. So what you do is is exactly the algorithm that we already used for nonlinear functions, for solving nonlinear equations before. So what you do is so what we do. So no, let's do. It doesn't matter, but it's more elegant to put minus here. So then the system that we get can be written as mx equal nx plus b. So iteration means that we take initial guess, or just some initial vector as zero approximation of the solution. And then what you can do for the next iteration, well, you substitute it here and then solve the system with respect to that x. So you use the old x on the right-hand side and find a new x on the left-hand side. And this gives you x1, etc. So the general equation for having k approximations, so you find the next approximation by solving this system. So you see you substituted to the right-hand side where we have this bad matrix n, but we don't need to solve anything, we just multiply. And then solve it with respect to good matrix M. So it gives you k plus. And you do it many number of steps, and you expect the expectation is that the sequence converges to some x as k goes to infinity. And if it converges, so you can make this limit on both sides, right? So then it means that the limit satisfies this equation, which is exactly ax equal b. Right? So if this sequence converges, then it gives you a solution. This solution. So the only thing we need is that it converges. So the definition is the iterative method that we just described is called convergent. So the convergence, the crucial point is that it should converge for some initial guess, which we don't know. We don't know what is good guess. So essentially the method is convergent when it converges for any initial state. If xk converges as k goes to infinity for any x0. So the method is convergent if it converges whatever initial guess you get. And it converges. And whenever it converged, we have a solution. So the converged value is a solution. So now I'll just give you the theorem which is used for proving convergence in various situations. So what is important about this matrix for making this method is convergent? And you see this method is actually is much cheaper than whatever other method like making LU decomposition, QR decomposition. This method is just you need to make, this method is based on the fact that you can somehow explicitly solve the equation for M. And then you just make iteration. So you may converge, as we will see, rather fast to the solution just with few iterations. And this will be way more optimal algorithm, so cheaper algorithm than any others. If the matrices are huge. So essentially, the central idea is that if the matrices are huge, this method becomes much more preferable. So how we do? So essentially, in order to see why and when it converges, so we write iterative relations for errors. Errors in the sense that let's call epsilon k is a difference between xk and exact solution x. So epsilon k will be essentially error of the approximation. So So X is this exact solution. So what we know is that xk satisfies this iterative relation. 1x satisfies the same relation, but in the exact form, in the form with the same x. And what we do, no. Okay, we multiply everything by m minus 1. So multiplying everything by m minus 1 means solving this system. And we know that we can solve it easily. So it means that technically you solve it. So essentially, for the proof, we just multiply by m minus 1. So this will be clean xk plus 1 equal b xk plus c. Let's see what it will be. So here b is m minus 1n, and c is m minus 1b. Okay, and then we subtract one equation from another. C will cancel, and difference between x gives epsilon. So we get a rather simple relation between, so I'll write it again here, between the errors. So every time if the error of the case approximation was this epsilon, so on the next iteration it will be just multiplied by this matrix B. Okay, so convergence means that epsilon k, which is b by the previous, so you can just as k goes to infinity. So the method is convergent if high powers of b multiplied by any vector converge to 0. And let's give you a theorem. Theorem which, so the following are equivalent. So there are three statements which are equivalent. So the first statement is that the iterative method is convergent. So it's the same as to say that the spectral radius of matrix B is smaller than 1. Remember that what is spectral radius? So it's maximum absolute value of the eigenvalue of the matrix B. So it should be less than 1. Okay, so here you already see the use of spectral radius, which we mentioned. And then C is related to the norm. There exists a norm, a matrix norm, Remember that it's a norm which is induced by special vector norm. Such that the norm of B is smaller than 1. Okay. So the method is convergence. It's the same as verifying spectral radius, and the same as is verifying the all possible ways of verifying special norm of some. You don't know which one, the matrix norm of the matrix. So let's prove. So proof. Okay, so take A, right? So if we have the method is convergent, okay, so what do we have? Then for any eigenvalue, you have B u equal lambda u, right? And that means that B k u equal lambda k u. And we need it to go to 0. It should go to 0 as k goes to infinity for any eigenvector u. So, not for any. So it should go to infinity for any vector, but in particular for that u. Okay, so eigenvector. And this means that absolute value of lambda should be smaller than 1. Because it's the only way how it goes to 0. And this is for any eigenvalue, which means that maximum eigenvalue, which is spectral radius, is also smaller than 1. Which is B. So we prove that if we have A, we have B, from A to B. Next, let's assume C. So if C means that for some norm, there is some norm which is condition. So then, okay, if we have C, then let's compute norm of epsilon k, which is by definition norm of bk epsilon 0. But this is a matrix, by the matrix norm, it's the same as B by the rest, norm of the rest, and so on. So essentially, if you make it iteratively, you can take this. Okay? And this is smaller than 1, right? By the assumption of the condition C, which means that this should go to 0 as k goes to infinity, whatever this vector is. So what we proved is that this is A. So essentially, between A, B, and C, here we prove that from A gives you B, and here we prove that C gives you A. So it will be closed if we. So it remains to prove this. So if you prove that B implies C, then we prove the theorem. So this will be exercise. And then it will be there. So there are, at the end of the message, that there are different iterative methods, which essentially are different on how you split matrix A to the part M and N, and also splitting it into the two parts, you need to have matrix M in a good shape so that we can solve easily the system with respect to this matrix. And the properties of N should be such that somehow we can control this B, that it's essentially controlling B, spectral radius smaller than 1 means that B should not be large. B should be somehow small, not too big. So if B is not too big, so that all eigenvalues are smaller than 1, then we can solve it iteratively. So all this collection of different iterative methods is how to make it. So different ideas how to make this splitting of the matrix and how to control them, or maybe some extension, some more elaborate version of this splitting. So I think that it's okay for today.